It's 1 o'clock. Let's go ahead and find a seat and we'll get started. All right, I'd like to thank everyone for coming today to our, I believe it's our third stakeholder meeting for Regional Groundwater Monitoring Program for our oil and gas here at the State Water Board. We have 5 presentations today from our esteemed colleagues at the U.S. Geological Survey and associated entities, and we're thankful for them to be here today. So we have a very full agenda. Just for your information, this is being webcasted and recorded. So if you missed something and you want to go back and watch it, or if you have a friend that was unable to attend, they'll be able to access that on our oil and gas website. For those of you online, please check your Outlook appointment for the URL for questions. There is no means of being able to ask questions without accessing that, so please email your questions, and we have staff that are reading those emails so we can read them out loud after each one of the presentations. In case of an alarm, we don't expect a evacuation drill today, but if you do hear an alarm, please exit through the nearest door, and our point of contact or reconvening is over across the street in Cesar Chavez Plaza Park. Right now, I'm going to turn it over to our senior of our oil and gas groundwater monitoring unit, Karen Kramer, who will introduce the next speaker. Thank you.
John. Thank you, John. I'm Karen Kramer, and I'm the Unit Chief for Oil and Gas Monitoring Unit. I'd like to introduce to you our first speaker, Matt Landon. Matt has been a geologist with the U.S. Geological Survey since 1990. He received his master's in geology from the University of Minnesota in 1993, a BS in geology from the University of Kansas in 1987, and he has conducted studies on groundwater hydrology and geochemistry in Minnesota, Nebraska, California, and Southeast Asia. He has been with the USGS California Water Science Center in San Diego since 2005 and is currently serving as the project chief for the USGS California Oil, Gas, and Groundwater Project that is being conducted in support of the State Water Resources Control Board's Regional Monitoring Program. So, Matt Landon, thank you.
Oh, thanks, Karen. Okay. So I'm going to just start off with thanks for everyone for being here today. And thanks also for folks who are online. And I'm going to start off with just providing a overview of what our activities have been for the regional monitoring program and an overview of the program. And so looking ahead at today's briefing, I'm going to start out talking about, or just a reminder about what the program is about, the status of the program, then we'll move into 5 presentations that'll include a presentation on the volume balance of current oil fields that David Shimabukuro will be presenting. Then we'll have 3 talks on regional groundwater monitoring results from 3 different study areas: Elk Hills North Coast Levee from John Warden, Oxnard study area from Celia Rosekrantz, Orcutt study area from Robert Anders. And then we'll have a presentation on radium in groundwater near oil fields in the southern San Joaquin Valley from Pete McMahon. And we'll have a closing wrap-up session where we talk about just an overview of some lessons learned in the program to date. And we'll give some preliminary results from the first of our multiple well monitoring sites that we drilled adjacent to oil fields, and this will present some preliminary results from the site that we installed near the Lost Hills oil field in 2018. So just as a quick reminder of what the regional monitoring questions are that are motivating the program, those include where are protected groundwater resources, how close are oil and gas operations and protected groundwater, and what geologic materials separate them, where is there evidence of oil and gas fluids and protected groundwater, and where does evidence indicate no connections? When oil and gas fluids are present in protected groundwater, what pathways or processes may be responsible? And have oil and gas operations as a whole contributed to water quality changes in groundwater basins relative to other processes that can affect groundwater quality? And you'll hear a number of examples of the different talks of addressing those questions today. Whoops. There we go. Okay, so let's review the general workflow for the regional monitoring program. Since 2016, we have been conducting studies in specific oil field areas. Each year we begin analyses in different oil field areas, several oil fields per year. These are multi-year study programs. Those study programs include several phases, including historical data compilation, sampling site selection based upon review of historical information, extracting information from geophysical logs for protected water mapping, sampling water and oil wells, data analysis, quality assurance and quality control of the data, ultimately leading to public data releases of all the information that we compile and collect. We prepare interpretive manuscripts describing the results of the study. And of course, we have public briefings where we present, roll out the results of studies that are nearing the wrap-up phase, of which today's meeting is an example. And then we have those products reviewed and published. We have been having stakeholder meetings, approximately 2 per year. We are completing the first set of study areas that began in 2016. And one of the talks you'll hear today from Pete McMahon will be reporting results of radium and groundwater from the first set of oil fields that we began study of in 2016. You'll also hear some talks from study areas that we began working in 2017, Elk Hills, North Coles Levee, Oxnard, and Orcutt today. And there also will be results from those study areas presented in future stakeholder meetings. And you'll also be hearing then, similarly, we began work in several new study areas in 2018. And those will have similar cycles of analysis and reporting in the future. And we're about to begin further analyses in additional oil fields in 2019. Some of the talks you'll hear also are describing the results of investigations at a larger scale. So the first talk you'll hear today from David Shimabukuro will be describing results of analyses of oil field fluid balances within oil fields in Kern County. And so this is a larger scale of investigation at the regional scale, integrating results of analyses in multiple study areas. And as the program continues, we'll be reporting out more and more results at those larger scales. So lots of information flowing, and updates on all of this is available on the websites for the program, and we'll have those websites up in a moment. Okay, so where have we been working? With the oil fields that we began working in 2016, we conducted sampling activities in Lost Hills, North and South Belridge, and Fruitvale, and conducted mapping of protected water in additional oil fields, including Elk Hills. These are the fields outlined in blue on this slide. In 2017, we continued with sampling activities in Elk Hills, North Coles Levee, Orcutt, Oxnard, and Montebello. You'll be hearing results from groundwater sampling from 3 of those study areas today. Protected water mapping also occurring in additional fields, including Midway Sunset and other fields that you'll be hearing about in future stakeholder meetings. Study areas in 2018 include Santa Maria Valley, San Ardo, Buena Vista Midway Sunset, Kern River, and Plaza Rita. We anticipate reporting out on the results of those analyses in future stakeholder meetings. So to get into additional information, you can go to both the Water Board and USGS websites shown here to get information on program descriptions, sampling protocols, published reports, published data, and summaries of findings. Just want to point you to some recent publications that have come out. These are, again, available from those websites. Several recent publications since the last stakeholder meeting in June of 2018. These include USGS reports on statewide prioritization of areas for regional monitoring and preliminary salinity mapping results near selected oil fields. Those were results described in stakeholder meetings in 2017. 2 journal articles, one on produced water chemistry in the southern San Joaquin Valley, and a study of salinity mapping in the Fruitvale-Rosedale Ranch area. Both of those products were described in public stakeholder meetings in 2018. And several more products are in press and in late stages of review right now. Since the last stakeholder meeting, we've had 8 new USGS data releases that have been published. This includes data used in statewide prioritization of fields to select for regional analysis, regional salinity mapping, groundwater chemistry data collected from 2 different oil field areas, historical produced water chemistry data from the Lost Hills Bell Ridge oil field area, and data used in salinity mapping in 3 different oil field study areas. So these and a number of other publications are available, and additional, because I noted additional publications on the way. So before moving into the talks, I just wanted to quickly note that in 4 of the talks you're going to be hearing today, you're going to be hearing descriptions of groundwater quality data. And I just wanted to set up that in all of these different areas and with these different topics that will be described today, we're using, the regional monitoring program is using a consistent set of analytes. So broadly, those analytes are shown on this slide. We're analyzing for a wide array of inorganic, radionuclear, and organic compounds, and are sampling for a number of isotopes and gases to try to understand fluid mixing, chemical sources, geochemical reactions, and age dating of groundwater. So those same analytes are analyzed generally for groundwater samples and oil field fluid samples. Some of the analytes can only be analyzed in groundwater, such as groundwater age dating parameters. And some of those analytes, the ones that are shown in red on this slide, are being used just for the regional monitoring program and have added considerable insight in some cases. So you'll be hearing some examples of some of those in the talks on the individual study areas. So with that, I think we're ready to move on to the presentations. Although certainly if there's any questions before we do that, be happy to take questions, either here or online. So, okay, thanks.
So while Matt's doing that, I'll introduce Dr. David Shimabukuro. David Shimabukuro is an assistant professor in the Department of Geology at California State University in Sacramento, where he directs the geology graduate program. His water resources group uses data science techniques to study hydrological systems throughout California. David's going to be speaking about the location, volume, and tempo of underground injection control in Kern County and possible fluid migration pathways. Thank you, David.
Thank you very much, Karen. Just wait till this gets started. And PowerPoint technical problems are harder than understanding aquifers in oil and gas fields. quick fix. So our group at Sac State has really been involved mostly with mapping salinity using geophysical logs and produced water data. But as we were going down this pathway, we realized that one part of the equation we really didn't understand was where injection is occurring and where those injected fluids are going. And this talk is an effort really to attack that problem of looking at these injected fluids and trying to come up with a creative way of looking, can we understand where injected fluids, injected water, and steam is going in the subsurface? So this work is done with my water resources group at Sac State. That consists of students, former students, and collaborators at the USGS and at other schools. So I think when we approach underground injection control and look at injected water, we ask this question of where is the water going? And in a typical oil field, for example, this one at Poso Creek, we'll look around, we'll see steam injection occurring, we'll see water disposal, water flood, and we really don't know where that water is going after it leaves that oil well. The standard approach is really to understand the hydraulic gradient field by looking at reservoir pressures, but those pressures can be really, really difficult to get. They're usually not publicly available. So the question we pose is, absent fluid pressures, absent publicly available fluid pressures, can we figure out where injected fluids are going? So we're going to use two data sources that I think are familiar to many of the people listening in. One of these is Dogger Well Finder. So what we did is we went back and scraped out all of the data in Dogger Well Finder since 1977. So this is the location of wells, this is volumes injected on a monthly basis, this is the types of fluids that are going into the ground. We processed this, it took a while. We have a pretty good data science group up and running at Sac State. The second data source that we use was the Dogger Cal WIMS database. And so this is data that's not as easily accessible, but it's useful information, including data such as the top and bottom perforation data of about half the wells in the state. There's a note in the bottom right-hand corner where you can see this Cal WIMS database has, for example, about 9,000 out of the 15,000 WF waterflood wells in the state that are in this file. So the question is, using these publicly available data sources, can we look at where injection is occurring and where it might be going? So just a quick overview of this data set. This data set, which we reduced down to Kern County only, covers the four major types of injection that are occurring. SC, which is cyclic steam, steam flood, water disposal, and water flood. As I'm explaining this, I'm going to group all of these together. And this might be a slightly puzzling choice, but my thinking is that once water is injected into the subsurface, once steam's injected to the subsurface and condenses, all the reservoir sees is water. And so all of these sources really in the end are water that has to flow somewhere. So we can look at tempo of underground injection control processes. I have several lines over here. Water production is the blue line at top. Water injection is the gray line just below it. The water injection is a sum of all these four other types of water, a sum of these four types of water injection: the disposal, water flood, steam flood, and cyclic steam. Okay? And you can see this in a time series, the change in injection volumes through time. We also can look at the Cal WIMS database and look at the depth that this injection is occurring. Here's the depth of the top perf, which can be used as a proxy for depth of injection for water flood, water disposal, cyclic steam, and steam flood. I think one of the surprising things is the shallow depth at which water disposal and water flood is taking place. We can actually combine the data on the previous slide, volumes, along with depth, to get a good idea also of how much is going into the formation at different depths. Now, we have these two data sets. We have volumes and depth, but one of the challenges is how to show volume and depth spatially. And I think a lot of us who use GIS have taken this approach, where we'll take injection sites, we'll color them by injection volume, and we'll come up with a map like this. Now, the problem with a map like this for Lost Hills is that, well, it's hard to figure out how much injection is occurring in any one spot. The density of injection is so great that these dots overlap, and 3 or 4 or 5 dots overlapping, it's really hard to figure out how much total volume is going down into the formation. And of course, that's the first step at trying to figure out where is this volume going. So we've taken a slightly different approach. We've taken the volume injected at each of these spots and spread it out over a small area. In terms of technical language, we spread this out under a Gaussian or normal distribution. So in the same way that an area can be spread out over a one-dimensional Gaussian or normal curve, you can take a volume and spread it out over a two-dimensional Gaussian curve. And so in this view over here, you can see a number of volume has been spread out over a spatial area, with most of that volume concentrated near the well. So we can do this with multiple wells. We can sum all of these piles of water together and then get a sense of how much water is going into the formation and where it's going into the formation. Now, when you first look at this, it kind of looks like water spreading away in a hydrological sense from a center. But I want to emphasize that at this point, this is just a way of visualizing and summing water volumes. In addition, we have to be careful because this is water volume that's going in, and water only fills up 25 to 35% of the rock volume. And so this water being injected into the ground piles up a little bit higher, quite a bit higher, because of the porosity effect. So what happens when you take injectors from a field and sum them together, sum up these spread out distributions of water? Here's an example of 3,700 wells from the Lost Hills field. And what we've done is contoured these piles of water by water height in meters. So you can see that in the center area where I've zoomed in, that these piles of water are up to 64 meters tall. In terms of scale for Lost Hills, in the upper corner, and I'm not sure if my cursor will appear. Yeah. In the upper corner, in terms of scale, this box is going to be 1 mile in terms of, it's a section, so it's a 1 mile scale. So that's a good, you can get a good sense of how large these piles of water are. So once again, this is what it looks like when we take this volume and spread it out over areas. You can get the sense of how we can see how much water is injected into the subsurface over here. On the left, we have the dots approach, and on the right, we have summed Gaussians. So with this, we can start thinking about, well, let's say water production. In this slide over here on the left is the water injection you just looked at with its peaks of 64 meters of water injected. On the right, you have water production. It's the same thing, that water coming out, the amount of water for each well can be spread out over a Gaussian. So what this approach allows us to do is we have water going in and we have water coming out in terms of volume. So we can take the difference between these two approaches. Two approaches. We can take injection and subtract production. So this is kind of a key slide for this presentation, because in this slide, we're looking at net injection. We've taken in the amount injected, subtracted the amount produced, and created this net map. So areas in red, for example, where this arrow is pointing, show large amounts of surplus injected fluid that was not removed via withdrawal, via production. Blue areas, such as these water source wells on the east side of the Lost Hills field, are areas where you have just much more production. So our conjecture, I guess, would be that these large red areas are net injectors, and they really act as fluid sources. The blue areas where fluid's being withdrawn are going to be fluid sinks. And one might suspect, because of volume conservation, that water moves from one area, from highs, from the red areas to the sinks, the low area, the blue areas. So how can we use this? Well, you might ask that water is injected at different depths, so how can we understand that? One of the powers of this approach is because Dogger has classified for many fields the depth of injection via what's called a pool code. In other words, what formation the water is being injected to. We can look at different formations within this field. So for the Lost Hills field, if we look at the shallow levels, we have the Tulare Formation and the Etchegoin Formation below it. So Tulare shallow, Etchegoin deeper. We're able to go through and split this data by formation or pool. So here's what's called the Tulare Etchegoin pool, pool code 10 by Dogger, 1,600 wells. And you might ask, Tulare Etchegoin, that's a mix between these two formations. Where exactly is that? Fortunately, because we have the Cal WIMS database, we have a good idea of the depth of top perf. So this image is going to be for 0 to 500 feet depth is going to be a majority of these injectors. So what you can see here is that most of that injection is taking place in the north part of the field. Similarly, we can do this with production. You can see that production for this Tulare Etchegoin, once again from 0 to 500 feet mostly, occurs along a longer part of the field. And taking the difference, what do we see? Well, for this particular pool, for this particular formation, we have this very large area of blue where you have excess withdrawal of water from this field. And this is kind of neat because withdrawal, well, what's going to happen? One possibility is fluids are flowing in, and we'll look at that. Another possibility is that if you withdraw too much, well, you're going to have subsidence. So it turns out that Lost Hills is a classic place for geodetics to show subsidence over oil fields. In this study from 1998, using INSAR, a satellite-based radar approach, subsidence rates up to 1 millimeter per day were found in the Lost Hills field. And what you can see, the locus of subsidence, the reds and yellows, if I go back, are in that area of the field where subsidence, where withdrawal dominates. So we're pretty excited that we can link up geodetic observations with fluid withdrawal. Now, let's go a little bit deeper. We looked at the Tulare Etchegoin. Pool code 27 is going to be just the Etchegoin, so it's going to be deeper than the last slides I showed you. We can do the same thing, water production, water injection. We're looking at about 1,000 to 2,000 feet depth now. So if we take the difference, what do we get? Well, the pattern's really different in the Etchegoin, in this deeper unit. These reds, what do they mean? Reds have net production, net injection, which means fluids are going down into this formation in excess. Because of volume conservation, this fluid has to flow somewhere else. And that's actually a big question, I think, for us thinking about this. Where might this fluid flow? Well, here's the two levels put together. So you can see the shallow Tulare Etchegoin with net withdrawal, the deeper Etchegoin with net injection. And so one of the possibilities is that these pools are really not containing the fluid that is being injected. Instead, there's some type of communication between pools. That injected fluid at depth is going into shallower levels. Fluid from the Etchegoin at 1,000 to 2,000 feet is going into the Tulare-Echegoin from 0 to 500 feet. And there's a reason to think that this might be the case by looking at the water cut, the water to oil ratio that's coming out of the ground. In this small figure, I have in red the deeper Echegoin, which has net injection. And then in green, I have the shallower Tulare-Echegoin. And what you can see here is that these reds and greens, the amount of water coming out of the formation relative to oil, they parallel each other. That in 2004, about 5 barrels of water were coming out for every barrel of oil in both of these formations. And by 2018, about now, 2019, twice as much water was coming out. And so these two formations with very, very different injection and production histories, what's going on is that the fluids in them are acting similarly, suggesting some type of communication between these two pools. So we can take this approach. We've written the code for this, so we can apply it to any oil field in Kern County or in any other county. It works best if a dogger has broken out these histories by pool. If they can't, well, we can still do it by field. Here's another example. Here's South Belridge. We do the same thing. Here's total water injection, total water production. We're going to take the difference. And what do we have here? For the South Belridge Tulare, which is distributed between about 250 and 1,250 feet depth. What you can see is there's this area in the northeast side of the field where there's a very large excess, a net excess of injected fluids over produced fluids. So I think there's a question there, and we'll leave that as an open question of where are those fluids flowing? Are they flowing toward the blue areas of net withdrawal? Or possibly could they be flowing outside the field? And I think that's a good area to look. This approach is powerful because we can also attack the problem by time. This is the Tulare-Echegoin, once again in Lost Hills, from 1981 through 1995 up through 2015. And what you can see here is that in the 1980s, this area had fluid balance, that there was an equal number of blue and pink spots. But as you moved into the mid-2000s, what happened is that the center part of the field had a large amount of net injection. And so when we're thinking about how fluids flow, we really have to take the time signal into consideration, that these fluids aren't static. And if we're thinking about the history of the field, that the hydrological conditions, the fluid pressures varied through time. And this approach by separating by year is a powerful tool in doing that. Those of you who are more visually oriented, since the Academy Awards were yesterday, you can imagine taking these slices and putting them into a movie. And so here's net injection. Reds are going to be net injection. Blues are going to be net production, going through time over the last 40 years. You can see the pinks coming in the middle of the field due to the injection that occurred at that time. Okay, so wrapping up, a few takeaways are that pool codes and depths that Dogger has on public record can be used to understand the 3D structure of injection processes. And that's going to be important because of the different behavior at different depths of injection. We suggest that this 2D Gaussian approach is a powerful way of summing multiple injectors. And when you have 10,000 injectors in a field, you probably need to start adding together the contributions. The difference between injected and produced volume will show net, and because of pure volume conservation, will show sinks and sources of water in the subsources. And these pathways possibly could be validated via water cut, like I showed, or via changes in log response, for example, or changes in salinity through time. So with that, I'll take any questions. Yes.
How many of the fields that are being investigated do you have pool information for?
So the question is, how many of the fields that we're investigating do we have pool information for? Right now, so Elk Hills, Lost Hills, Bell Ridges are good. Midway Sunset is probably the worst with pool code attribution. So for fields where we don't have pool code, one way of attacking the problem is by going after directly going after the depth of injection. So although the Dogger record, the perforation database is incomplete, my group's been going through, in collaboration with the USGS, in picking out the top and bottom perfs, so then we can still address the depth of injection for fields where we don't have pool data. Yep.
I have a question.
How come the cyclic steam injection numbers are so bad in terms of the fraction that you have data on in CalWIMS? Do you have any idea?
So the cyclic steam data, we think it's bad because that data can be determined. The top producing perf and the top injecting perf are the same thing. And so the CalWIMS database, and once again, this is from what we can tell, is focused on injection. And so our guess is that they had a secondary source of production top perf in some other database that was not linked together. So, so that's our best guess. So.
Quick question. How did you treat wells that were screened across both intervals between the Tulare and the Edgecoin?
So we used the Dogger pool code for this, the data that I showed you. So we just let Dogger, whatever Dogger called the injection pool, that's what we used. And I think that is it something we need to look into a little bit more? Which ones are crossing the Tulare Edgecoin? I think so, but once again, we're just using the Dogger data.
We have a question from the email. Preston Jordan with Lawrence Berkeley National Lab asks, were the Gaussians summed on a raster? If so, what dimension was each raster?
The rasters for this particular study were 10 meters. And the actual spacing of the Gaussian from a technical viewpoint, the sigma was 100 meters.
Okay. So next we have John Warden. John Warden is a hydrologist with the USGS California Water Science Center in San Diego. He joined the survey after completing his PhD at the University of Texas in 2016. His current projects include studies of groundwater quality and microbiology in the San Joaquin Valley and Mojave Desert, California. And so John is going to be speaking about regional groundwater monitoring results near Elk Hills and North Coles Levee. Give us a few seconds to set this up. Jennifer?
Thank you. Let me bring up my pointer. Yes, I'll be discussing the groundwater quality results of the regional monitoring program for the Elk Hills and North Hills Levee study unit. Some background, Elk Hills was discovered in 1911. It's produced more than 2 billion barrels of oil, which makes it one of the most productive fields in the US. It's also the largest natural gas producer in California. North Hills Levee, it was discovered in 1938, and it's located just to the east of Elk Hills. The aqueduct, just for visual orientation, the aqueduct runs through these study units right between Elk Hills and North Hills Levee. So our study area, these fields are located in Kern County in the southern part of the San Joaquin Valley, about 20 miles west of Bakersfield. The study area includes a 3-mile buffer surrounding the fields. That's shown as a dashed line in this figure and in subsequent maps that we'll show. These fields are classified as high priority for monitoring, a statewide assessment of oil and gas fields. The high priority fields are shown in orange in this map. So Elk Hills and North Hills Levee, they were classified as high priority because of the density of oil and gas wells. There are over 10,000 new active and idle wells in these fields. Those are shown by the blue dots, very high density. And there's also over 5,000 plugged or buried wells. Those are shown as the yellow dots. They were also classified as high priority because of the volume of fluid injected. So the upper figures in this plot, in this slide, are showing volumes of injection, produced water, and oil through time from 1977 to 2017 from Dr. Schmidt-Garrell's data set. The yellow is the injection line. The lower figure here is showing cumulative volumes over that time period. So from 1977 to 2017, there's been over 3 billion barrels of water injected into these fields for both enhanced oil recovery and water disposal. Okay, so moving to the major questions. So the goal of this study is to determine whether or not there's evidence of oil and gas fluids in protected groundwater. If there is evidence, we're going to identify the locations, look at what that evidence is, and look at possible pathways between oil, gas, and groundwater. And the figure on the right illustrating is some of those potential pathways. We're also going to look at the primary processes influencing water quality in the area, and we also want to discuss gaps in available information. And so in these studies areas, the fields cover large areas and water quality is not always available everywhere. And those are the main data gaps. So this is a high-level summary of the results for Elk Hills and North Hills Levee. We'll dig into this deeper as we go through the talk. So data from most wells showed no evidence of oil and gas constituents in groundwater. 3 of 32 wells sampled had some evidence of oil and gas fluids, and we'll talk about those. When evidence of oil and gas fluids were present, the indicators had low concentrations, which suggests mixings with small volumes of oil and gas fluids, and it's very localized, so it's local to specific wells, and not a regional process. Our approach is we sampled 32 groundwater wells and 1 groundwater banking pond. Sampling took place in summer 2017 and wrapped up in spring 2018. We analyzed for constituents selected to assess whether groundwater quality is influenced by oil and gas fluid. And we also looked at oil and gas activity near our sampled wells. So for example, we counted the number of production and injection wells within 500 meters of sampled wells. We also compiled and evaluated historical water quality data. The historical data mainly consisted of TDS and major ion concentrations in samples collected from 1925 to present. And from this task, we found 242 different wells or sites. We evaluated data from all those wells, and this turned out to be really helpful for evaluating newly collected samples and understanding baseline water quality in the system. Okay, in this slide, this is a map showing all sites with water quality data that we looked at. The newly collected samples are shown by the larger symbols. And so we sampled 26 monitoring wells. Those are the green circles. 2 public supply wells. Those are the blue triangles. 4 irrigation wells, the purple diamonds. We also sampled a groundwater banking pond, and that's the yellow square. And then maybe barely showing up are the small circles. That's the 242 different historical water quality sites. It's moving into results. This is a map showing groundwater total dissolved solids across the study area. It includes both new samples and historical data. In this figure, circle size corresponds to well depth, with larger circles indicating deeper wells. The color corresponds to total dissolved solids, with fresh in blue, brackish in green, and saline in yellow. And so the main takeaway with this slide is that there's a large range in TDS across the study area. Fresh groundwater, the blue circles, that's mostly groundwater recharge from the Kern River, which flows from east to west across the study area. Here's the Kern River. The brackish groundwater, the greenish circles, that's typical of west side groundwater in the San Joaquin Valley. That's mainly located in the western and southerly portions of the study area. And we also identified some saline water in shallow wells located near the edge of the Buena Vista Lake bed, which is located in this area. At this stage, we think the saline water is related to evaporative concentration of water and water-rock interactions in the aquifer. That's a subject of ongoing study. Okay, moving into sites with evidence of oil and gas fluids. So this slide is showing the different samples that had evidence of oil and gas fluids. We're going to go over this in detail in the next couple slides, but the table is kind of useful for looking at our thought process. And so the first column are the different wells. In the solid text, those are sites that we're confident have evidence of oil and gas fluid. The gray italics, those are inconclusive wells. They had some evidence, but not enough to make that determination. In the second column, this is our different evidence. There are different constituents that we're using to make the determination. And I want to emphasize that we're looking for multiple lines of evidence before we come to any conclusion. And so our different constituents, the definitions down in this box in the bottom. So VOCs, that's volatile organic compounds. Some VOCs are associated with hydrocarbons. DOC is dissolved organic carbon. Oil reservoirs have high DOC. And then CH4 is the methane. Methane can be produced in aquifers or originate from oil reservoirs. We also looked at the age, or the time since the water recharged the aquifer, and oil and gas activities near our sampled wells. Okay. Okay, so we're going to go through the different sites with evidence of oil and gas fluids in this map, starting with COLN-9. So this was a deep monitoring well. We detected hydrocarbon VOCs, including some benzene, toluene, and xylene compounds. Water in this well is pre-modern in age, which means it was recharged prior to 1950. There were no other oil and gas indicators in this well. And so combined, these data are suggesting that there's a leaky oil and gas well or some other subsurface pathway for the pathway between oil, gas, and groundwater. The next well, COLN-6, this well had unexpected TDS and ion ratios for its location in the flow system. The TDS was more than 1,000 milligrams per liter higher than nearby wells of similar depth. The ion ratios in this well were consistent with mixing with produced water. We also detected a VOC, and this well was pre-modern in age. And so to combine these factors suggests that the source of oil and gas fluids in this well could be a leaky oil and gas well. The third and final site, Elk 7. This was one of the shallow wells located on the edge of the Buena Vista Lake bed. We detected one hydrocarbon VOC in this well. Dissolved organic carbon was much higher than nearby wells of similar depth, and the same goes for TDS. This well was mixed age, and so that means it contains a proportion of modern groundwater recharged after 1950, and this suggests infiltrations of activities from the land surface. And so historical oil development practices in this area sometimes released produced waters to stream drainage networks, which drain to the Buena Vista Lake bed where this well is located. So it's one possibility. I just want to touch briefly on some of the samples with inconclusive evidence. So down on the eastern edge of North Coles Levee, this well, COLN-17, it had unusual TDS and ion ratios for its location in the groundwater flow system, but it didn't have any other oil and gas indicators, so we weren't able to be conclusive that was related to oil and gas fluids. Similarly, 2 deep wells located kind of off the northeastern edge of Elk Hills had ion ratios consistent with mixing with produced water or west side groundwater. There was also some evidence of methane in these wells, but the methane concentrations weren't high enough to determine whether or not the methane originated in the aquifer or in oil reservoirs. Okay, so moving on. So as mentioned earlier, we looked at oil and gas activity near newly sampled wells, and this map is showing sampled wells with oil and gas injection volumes. And so the injection volumes are shown by the brown circles, with circle size increasing with injection volume. And so of our 3 wells, we had 1 well that was located within 500 meters of 7 injection wells. We also looked at production. It was located within 500 meters of 11 production wells as well. So these could be possible sources of oil and gas fluids in that well. All right. So this slide summarizes the potential pathways between oil and gas and groundwater in wells with evidence of oil and gas fluids. We have our 3 wells. So Elk 7, we think that could possibly be related to activities at the land surface, and that's shown here as the schematic with the legacy surface disposal. We also have COLN-6 and 9. Those could be related to leaky wells. So we have leaky production well here and injection well here. I'm just looking at that in a visual schematic. Okay. We also looked at processes influencing groundwater quality not related to oil and gas activity. And there were 3 interesting things that we found in this part of our analysis. There we go. So near the southeastern edge of our study well, there were 4 irrigation wells that had increasing TDS through time. The data set was from the 1950s to the present, with samples collected every 10 years or so. TDS went from about 1,000 to 4,000 milligrams per liter through that time. There were no oil and gas indicators in those wells. They're also pre-modern in age, and they're long screen monitoring wells. They're screened from 300 feet to 1,000 feet in depth, approximately. So we think what's happening is that declining water levels in that area are increasing the proportion of deeper and saltier water in that well, which leads to increasing salinity. We also found strong evidence of groundwater banking. And so there are groundwater banking operations in the northern half of North Coles Levee and just to the north. So these were indicated by low TDS values, modern and mixed stage groundwater, which is kind of unusual for the study area. The ion ratios are also consistent with aqueduct and Kern River water, so all of these data lead to the interpretation of recharge from water banking. And then finally, we found some evidence of irrigation return flows. So this well, COLN-7, located at the northeastern edge of the study area, had increasing TDS and nitrate through time. However, the TDS was quite low, less than 500 milligrams per liter. And the oxygen and deuterium isotope composition also increased through time. And this water from this well was of mixed age, which combined, these factors suggest irrigation return flows in water from that well. Okay, so moving forward, in the last couple of slides, we're going to look at information gaps. And so this map shows all oil and gas wells mapped on top of newly sampled wells. And what we can see here is that for Elk Hills, there's a spatial gap in the distribution of groundwater wells. There's not much information on groundwater levels or quality off the flanks of the oil field. We were able to sample 5 shallow wells. These are less than 100 feet off the southeast corner of Elk Hills, but we don't really have information or recent data for the deeper groundwater flow system. This is in contrast to North Coles Levee, where we were able to sample wells in close proximity to to oil and gas wells. However, there's a large vertical separation at North Coles Levee. And that's what we're going to look at in this slide. So on this slide, the y-axis is depth. And so the Elk Hills oil and gas wells are shown in green, and North Coles Levee oil and gas wells are shown in yellow. And then on the x-axis, we have longitude. So you can imagine just sitting at the southern end of the San Joaquin Valley and looking at a west-east cross-section, looking north across the study area. And so in North Coles Levee, our groundwater wells, the deepest wells are around 1,200 feet or so, and then production is happening at greater than 7,500 feet, mostly. So we don't have information on water quality across this vertical gap, if you will. Okay, so in closing, here's a summary of our findings for Elk Hills and North Coles Levee study unit. 3 of 32 groundwater samples had evidence for the presence of oil and gas constituents. When present, when present, it was local and low level. The most useful constituents for this study unit included historical data, major and minor ions, VOCs, age tracers, and oil and gas activities were helpful explanatory variables. The data gap is largely spatial for Elk Hills and vertical for North Coles Levee. Looking at other processes influencing groundwater quality in the area, the major recharge sources included the Kern River, west side groundwater, and water banking activities. We saw evidence of irrigation return flows and declining water levels that might be affecting water quality. And we also identified high salinity shallow groundwater near the Buena Vista lake bed. With that, I'll take any questions. Thank you.
Hi. So I was just kind of curious for the North Coles Levee. You had a couple wells that had pretty low levels of VOCs, and you concluded those were leaking oil and gas wells. But I mean, could it also be possible that there is oil that's in lower concentrations at those depths? I'm not familiar with the geology of the area, but I did see on your map that there was one oil and gas well that looked like it was completed within the same range as the groundwater wells. Did you look at kind of the driller's logs for some of those oil and gas wells, see if there had oil shows at shallower depths that may just not have been producible?
Yeah, I think that's certainly possible. Yep. So it could be, it could be a leaky oil and gas well, or it could be some other subsurface pathway or natural, naturally in the reservoir.
Okay.
And aquifer, yeah.
And just also out of curiosity, for those wells, what was the nearest oil and gas well? Were they in close proximity or they're further away?
So in North Coles Levee, so we looked at 100 meters and 500 meters. So there had been nothing within 500 meters for that particular well. Now there are, I don't have the exact number, but around maybe 1,000 meters or a little bit further, there would be wells in that area. Now in North Coles Levee, production depths are much deeper, of course. So that's another factor to consider. But yeah, looking at well logs could be useful.
All right, thanks.
Yeah, thank you.
We have a few questions from the email. Preston Jordan with Lawrence Berkeley National Lab. He thanks you for the talk, and his first question is, Elk Hills is unusual in having substantially more gas injection than any other oil field in the state. So much that its gas handling is akin to one of California's 2 large gas storage facilities. Was this considered in prioritization and fluid balance?
So the prioritization looked at injection volumes and density, and that's the reason for classifying Elk Hills as high priority. And what was it?
And fluid balance.
Fluid balance. I'm not sure how the gases were handled in the fluid balance, but maybe if Dave is still around. Maybe. Oh, yeah.
There you go. There you go. Sorry.
For Elk Hills, we've only studied the Tulare, so at that point, gas gas is not part of the equation, so we haven't treated the deeper reservoirs.
Okay. Thanks.
Okay, the second.
I have one more addition to that. Hey, Preston, it's Kim. When we did the prioritization, we only looked at the fluid injection. That was a preliminary first cut.
The second question, did injection production well counted near sampled wells consider the depth of those wells?
I don't think so. I think it was just all injection and production wells within that distance of 500 meters. Those were all counted, and the injection volume was then summed up for those particular wells. I don't think depth was a consideration, if I'm understanding correctly.
Okay, the third question, could detection in the first well described be due to natural seepage rather than leaky wells?
Yes, I think that is a possibility. Yep.
And the final question is, for North Coles levee, were shallower water source wells used by the upstream company for water flooding the production zone considered?
That was considered, however, we don't have water quality data near that area where those activities are occurring. And so that highlights one of the gaps that we were talking about at the end. There's a spatial gap. We don't have data in that area to make that determination or to look at that process. Thank you.
Thank you, John. Okay, well, we're going to take a short break, a 15-minute break. Let's regroup at 2:20. Just want to let you know that we also have a sign-in sheet in the back of the room, so please sign in if you have a chance. And there's copies of abstracts and also coffee and water. Help yourself. Thank you. we're going to get started again. Okay, before we start with the next presentation, we have a couple of questions that came in a little late on the email. So the first question is for David Shimabukuro.
This is also from Preston Jordan, and he asks, the volume of water to perk ponds had a discontinuity across 2015 due to discovery and rectification of miscoding by companies during the SB4 study. How would this impact the results, or was there a way around this?
So we looked at injection volumes and then production volumes on the WellFinder database. There's a question of how do we know that the data is accurate, that the data reported by producers is accurate. And we found that that water cut is probably a pretty good indicator in that oil is going to be hopefully reported correctly. Water, there's some question about it, but if the water to oil ratio behaves in a predictable fashion, then it's likely that the water data is accurate. Anytime the water data is inaccurate, it appears that the water cut looks really strange, like you might have water cuts go down to near zero or up to in the hundreds. So that's water cut is a first order quality control.
And then for John, he asks, but did you look at the gas injection as well as the water injection in the prioritization?
The prioritization was just a first cut prioritization, and it looked at density and injected volumes. Oh, water injection, sorry.
Okay, thank you. Our next speaker is Celia Rosecrans. Celia is a hydrologist with the USGS in Sacramento. Celia has a BS in geology from the Evergreen State College in Washington and an MS in hydrogeology from California State University in Sacramento. Her primary interests are geochemistry, fate and transport of geogenic constituents in groundwater. Her recent work includes three-dimensional continuous probability models for aspects of redox conditions, manganese, and pH in the groundwater system of the Central Valley, California. So Celia will be speaking about groundwater quality results in Oxnard. Please help me in welcoming Celia Rosecrans.
Thank you, Karen. I hope you guys had a nice break and everybody got a cookie. So today I'll be presenting the results for our Oxnard study unit. The Oxnard oil field was discovered in 1937 by the Baca Oil Exploration Company, and they drilled down about 2,800 feet to tar sands. These tar sands are above one of two formations in the Oxnard oil field. As of 2017, this oil field has produced about 10 million barrels of oil. The Oxnard oil field lies within Ventura County, just east of the city of Oxnard, and it's classified as a high priority based on its vertical proximity of aquifers and hydrocarbon reserves, and as well as the high volume of injection for water disposal. Shown here is a cross-sectional map of the reservoirs within the Oxnard oil field. Reservoirs are found at depths greater than 2,000, and that's here at the Monterey. And above that, you can see in green where that Baca tar sand sits, and then the deeper formation is the SWRCB formation, and that's found at depths greater than 6,000 feet. I want to bring your attention to this cross-section AB or across the top here. In this next slide, I'm going to relate that in plan view, and I've color-coded the oil and gas wells by depth so you can see where they lie. The blue wells are the 0 to 2,000 depth, and that's tapping that Baca tar sand that I showed in the previous slide. The red is the deeper 6,000 feet wells that tap the SWRCB, and the green are intermediate wells. The gray are wells which we don't have any well preparation data for. This next slide shows the volumes of injected water and produced water and oil in the top graph from 1977 to 2017. And below we have the cumulative volumes. Water disposal injection in the dark orange on the bottom makes up for about 72% of total injection in Oxnard. And the remaining, that portion in the lighter orange, is cyclic steam. Interestingly, at this production, or at this oil field, about 20% of the production comes from just 2 wells in the southwest corner of the oil, or southwest portion of the oil field. These are water disposal sites. And it's my understanding that their permit expired at the end of 2018. And these are the locations of those water disposal sites. So before I present the summary of our findings, I wanted to give you a little historical background about the Oxnard Plain because it's relevant to the summary of our findings. So here in the center, I have the Oxnard oil field boundary within the Oxnard coastal plain. The Oxnard aquifer consists of an upper and a lower aquifer with a depth delineation of about 500 feet. And historical groundwater began in like the 1930s, and over time it resulted in groundwater overdraft. And this resulted in seawater intrusion, vertical increase vertical connectivity between the upper and lower aquifer, as well as, I lost my train of thought there, sorry. As well as seawater intrusion, and a change in regional groundwater flow paths from natural groundwater flow paths to centers of where they groundwater discharge areas. The other thing that's important in this historical overview is that there's a lot of high chloride concentrations associated with seawater intrusion, agricultural return flow, and deep formation brines. And the third piece that's important is an area east of the Oxnard oil field, which is in Pleasant Valley, shown here in green. And this area has been known to have high chloride concentrations in the deeper aquifer portions of this area due to marine formations as well as known hydrocarbon reserves. And historical studies have shown that deep wells in this area have a similar water composition to oil field production water, and that this is due to water development and not due to oil and gas activities. And in 2017, we sampled several wells in this area, and we found a similar water composition to the historical values in terms of chloride, DOC, and some of the isotopic composition. So I'm going to move on to our 2017 sampling, and here we have 14 wells that we sampled within the Oxnard oil field, shown here in pink. There's a 3-mile buffer area around that Oxnard oil field. The blue wells are our 10 wells that we sampled in the lower aquifer system. The red triangles represent the upper aquifer system, and the diamonds represent the wells that were sampled across the aquifers. The black wells, of course, are the oil and gas wells. And if we look at the historical data for this area, we were very fortunate that we had quite a bit of historical data with well construction data shown here in gray. And that was really key to understanding some of the groundwater processes that were occurring in the system. And then we also have groundwater level contours provided from us from United Water Conservation District, and these are shown here for the lower aquifer system with the general direction of flow. And the last piece of evidence, or the last thing that we used here, I wanted to say that we had 4 monitoring wells, 10 production wells, and I think that, yeah, that's it. And so For the this slide here, I wanted to introduce you or remind you to some terms that I'm going to be using to summarize our results. The first is thermogenic gases. These are thermogenic gases come from oil. Thermogenic gases are produced at depths greater than 3,000 feet, and they include gases as methane, ethane, propane, butane, and pentane. Whereas microbial gases come from bacteria eating organic material, and microbial gases are found in aquifers and they predominantly occur as methane. So I'll be using these two terms to summarize some of my results, so I just wanted to familiarize you with some of them. The results of our sampling found that we had no evidence or no detections of petroleum hydrocarbons, inorganic constituents, or isotopes that indicated we had oil field water mixing with the groundwater overlying the oil field. But here I show that we did have methane detections in 12 of the 14 wells. And from the previous slide, we know that methane can be produced both from biogenic and thermogenic sources. So we use isotopes, particularly in this example I'm going to be using and talking about the carbon-13 isotope of methane to further discern where these sources of methane are coming from. So if we take that closer look and zoom in a little bit on some of these wells, we see that ZR5 is one that had the highest methane, and it's also located in that high density of oil and gas wells shown by the little gray dots. Its methane concentration was 9.1 milligrams per liter, and it also has a carbon-13 methane isotope measurement that falls in that thermogenic range. The second well was north of that. ZR7 had a lower methane concentration, but also showed a thermogenic gas signal. And the third well, ZR6, had a higher intermediate methane concentration of 5.1 milligrams per liter. But the isotope concentration of this is more of a mixed signal. It's not as strong as a thermogenic signal as the other two. So we found that we had 2 thermogenic wells and 1 mixed well in this work. And we continued to look at this, and we looked at some of the other thermogenic gases for these wells. And we see that we also have, for ZR5, we have detections of propane, isobutane, pentane, and then in the other wells we have detections of propane and ethane. And we hypothesize that the sources of these thermogenic gases are coming from wells or well bores migrating up in areas of high density oil and gas, or that it's just thermogenic gases are migrating up from the Vaca tar sand. So now that we know which wells that we have these thermogenic gases, we start to look for multiple lines of evidence in terms of how these wells are, or why we're seeing these gases in these wells. So the first thing we did is we looked at oil and gas activity within 500 meters of groundwater wells. So when we do that, we draw a little 500-meter buffer around these wells, and we see that several wells have no activity around them, and we zoom in on some of the ones that we did capture. And these 3 wells here, which are wells that had the thermogenic signals, capture quite a few of the wells that have activity in them. Take a closer look at those. ZR5, this is our well that had the strongest signal, has 12 plugged or abandoned oil gas wells within 500 meters, 26 active or idle oil and gas wells. It also has 32 injection cyclic steam wells with the cumulative volume from 1978 to 2017 of 3.3 million barrels. Where ZR14, this is those 2 water disposal sites. That was within the 500-meter buffer of the ZR14 well that we sampled. And that has 9.7 million barrels of water injected, has 13 plugged abandoned oil wells and 1 active oil and gas well. And these 2 to the northwest just have a little bit more than a handful of plugged and abandoned gas wells. Second line of evidence that we looked at was just looking at the vertical proximity of groundwater wells to oil and gas wells. So I showed this slide earlier. This is our 14 wells to the right, and then the gray dots are that historical data set. So I've plotted those wells on the left-hand side depth to bottom of perf wells, and shortly I'll be putting oil and gas wells on this, against longitude. So you can see the spatial distribution both in the XY direction as well as plan view. And as I step through these slides, I have these color-coded, so hopefully you can kind of make the connection vertically and spatially as we look at these wells. So the first set of wells I'll add are the oil and gas wells in terms of their status. They're color-coded active, inactive, and plugged, and you can see that we have a cluster of active and inactive wells here. These are associated with the cyclic steam wells in the Baca tar sand, and we have these here that hit that deeper Sespe formation, and then in plan view where those are located. And then we can also look at the well types. So here in purple, we have cyclic steam. And then we have the water disposal sites in green, and then the oil and gas in black. And you see here on this side as well, we see the cyclic steam. And if we add the wells where we had the thermogenic signal, I can outline those, and these are the 3 wells here. They line up approximately on the same line of longitude, and so they're kind of stacked up here vertically. And you see that they lie above the cyclic steam activity, and they're associated with that, and not with the deep injection high volumes at the deeper depths. So to summarize our results, we had deep brine signatures that we talked about east of the oil field were not detected in any of the wells overlying the oil field. We had thermogenic gases detected in 2 wells overlying the oil field and possibly a third. That was that mixed signal well. Thermogenic gases occurred in deep groundwater wells with the highest concentrations associated with those high density wells and shallow oil development. And thermogenic gases probably resulted from just stray movement along preferential pathways, such as wells or just migrating up from the formation. And in the Pleasant Valley area east of the Oxnard oil field, we also detected those deep brine signatures, and the values were similar to historic data. And again, those detections are related to groundwater overdevelopment rather than oil field activities because they have a very unique signal in terms of chloride, DOC, and isotopes. Some other factors that are important in Oxnard that affect groundwater are just managed aquifer recharge to the north. This is water that's added to keep a hydraulic barrier in terms of keeping the coastal intrusion or seawater intrusion in the upper aquifer at bay, and also it provides a substantial groundwater replenishment to coastal coastal groundwater withdrawals. We still do see a little bit of seawater intrusion from the southwest, but it really hugs that coastline, and it's generally just in the upper aquifer system. Agricultural return flow is an important thing that affects groundwater quality in terms of TDS, particularly for long screened wells where the top of the screen intercepts the upper aquifer system. And then upward movement of deep brine formations in response to groundwater development is something that will affect groundwater quality in Oxnard. Here's some information gaps and priorities for future monitoring. We have little historic data on light hydrocarbon gas concentrations and isotopic compositions. We really need to sample further in terms of groundwater wells and oil within the area to truly determine those sources and pathways of thermogenic gases. And then maybe some of that sampling could include long screen irrigation wells or installing multiple well monitoring sites. And then I've listed here some useful constituents that I think that we should include or that would be very helpful: light hydrocarbon gas concentrations, some minor and major ions, water and carbon isotopes, and then potentially some noble gases, which are in progress. We do have some samples hopefully coming back for the 14 that we sampled during the 2017 sampling. So I would take some questions. Thank you.
Let's give it a few minutes
right.
for the computer questions to be emailed in.
Okay,
Maybe just
move on.
over.
Okay.
Yeah. Gonna get this set up. And you want this. All right. So our next speaker is Robert Anders. Robert is a research hydrologist with the U.S. Geological Survey. During his 20-year career with the USGS, Robert has focused his research on the application of water quality and environmental tracers to develop a more comprehensive understanding of the fate and transport of anthropogenic contamination associated with regional groundwater systems. Robert's educational background includes receiving his BS and MS in geological sciences from San Diego State University and a PhD in civil engineering from the University of California, Irvine. Thank you, Robert.
Excuse me. Okay, so I get to do the third of these results presentations. My talk this afternoon will present the results from the Regional Groundwater Monitoring Program for the Orcutt oil field. The Orcutt oil field was discovered in 1901 and is a large oil field located in the Solomon Hills south of the unincorporated town of Orcutt in Santa Barbara County. So I'm going to do this. Okay. The Orcutt oil field is classified as a high priority oil field based on total volume of injection for enhanced oil recovery and waste disposal. Other potential risk factors, oil well density and vertical proximity of groundwater and oil resources were moderate. Okay. This map shows the oil well density in the area of the Orcutt oil field, okay? The oil and gas wells within a 3-mile buffer of the oil field and the oil field administrative boundary. According to information compiled from Dogger online database, the Orcutt oil field contains 455 active or idle wells, and 257 plugged or buried wells. And these wells exist mostly in 8 sections in the northern part of the oil field. And so basically, here's the area. I'm sorry, yeah. That's not working. No. So, and associated with oil field density is consideration of oil well development. This map contains the spud or construction dates for the small subset of active oil wells in the Orcutt oil field to illustrate that early oil well development resulted in hundreds of oil wells before 1978, when construction practices were less comprehensive in regards to cemented intervals to protect groundwater and provide potential pathways for contamination. Shown here is a cross-section, of course, the Orcutt oil field and a table of injection wells for the major oil pools. As we can see from the table, the greatest injection volumes for the enhanced oil recovery and waste disposal occur in the Monterey Formation. Okay. At depths between 2,000 and 4,000 feet, with smaller injection volumes for enhanced oil recovery into the shallow diatomite and SX units of the Siskiyou Formation. And also shown by this red line is the bottom of the Paso Robles and Callejas formations, which make up the primary groundwater aquifers in the area. However, more recently, due to the onset of cyclic steam injection, the shallow diatomite unit has become a more targeted zone for oil recovery, resulting in increased frequency of oil seeps possibly related to oil extraction activities occurring in the area. And finally, looking at the regional groundwater flow, contours of the elevation of water table indicate groundwater flows to the southwest into the San Antonio Creek groundwater basin and northwest into the Santa Maria groundwater basin from the oil field, from the oil field, which straddles the two groundwater basins. Okay, so with that background, the overall summary for this particular study unit is that 4 of the 16 wells that we sampled as part of the monitoring program were found to contain geochemical indicators of oil-filled fluids mixed with groundwater. 1 well had concentrations of inorganic and organic constituents consistent with produced water. 1 well had concentrations of inorganic constituents and carbon-13 isotopic values, which were consistent with produced water. And 2 wells had methane isotope values and concentrations of inorganic constituents and light hydrocarbon gases, which were consistent with oil-filled fluids, which are produced water in combination with thermogenic gases. Okay. So before I get more into the results, let me just describe that the design of the regional monitoring program for the Orcutt oil field included a collection of 16 groundwater samples from 7 domestic, 6 irrigation, and 3 monitoring wells between September 2017 and July of 2018, along with produced water samples from 5 oil wells and 1 injection site. And those are shown with the solid symbols. We also use historical data from 27 other groundwater sites sampled in 2017, 121 sites with older groundwater sites, with older groundwater data, and mostly inorganic chemistry data from 25 produced water sites. Okay, and this is a look at the total dissolved solids from both the historic and new data. And it reveals that most of the groundwater in the area of the Orcutt oil field had TDS concentrations which were less than 1,000 milligrams per liter, with some samples between 1,000 and 3,000. Also shown are the locations and names of the 4 sites which had the geochemical indicators of oil field, which have geochemical indicators of oil field fluids. These 4 sites had TDS concentrations between 1,000 and about 8,000 milligrams per liter. So this is, in addition to the TDS, would be considered a comprehensive list of the geochemical indicators of oil field fluids that were present at the 4 groundwater sites in the area of the Orcutt oil field, along with their age and locations. So I'm just going to briefly go through this just to identify them, and then we'll take each site individually and I'll discuss them in more detail. So ZR16, which is the site that had the highest TDS concentration, it's located adjacent to the oil field and had measured chloride, sulfate, iron, dissolved organic carbon, and methane concentrations which were greater than the mean groundwater concentration. Other geochemical indicators present at this site included minor ion ratios and detection of 5 dissolved petroleum hydrocarbons. Also at this site was detection of 28 manufactured volatile organic compounds not associated with oil field activities, and suggest that this site is affected by an industrial source of chemicals as well. For CR13, the second site located adjacent to the oil field, had TDS, chloride, ammonia, dissolved organic carbon, and methane concentrations which were greater than the mean groundwater concentration, whereas sulfate was less. Other geochemical indicators at this site included minor ion ratios and enriched carbon-13 isotopic values. The groundwater age of ZR13 was determined to be pre-modern or having been recharged prior to the 1950s, and that's defined as carbon-14 activities less than 80% modern and a non-detectable level of tritium. At ZR3, which overlays the Orcutt oil field, the geochemical indicators included TDS, chloride, sulfate, dissolved organic carbon, minor ion ratios, methane concentrations, and isotopes, and light hydrocarbon gases. And finally, at ZR2, overlaying the Orcutt oil field, the geochemical indicators include TDS, chloride, sulfate, ammonia, dissolved organic carbon, minor ion ratios, methane concentration isotopes, and light hydrocarbon gases. And these two sites were also determined to have pre-modern, were also determined to be pre-modern in age. Okay. So based on a list of geochemical indicators, evidence of produced water at ZR16 is provided by the major ion chemistry, trace metals, dissolved organic carbon, minor ion ratios, light hydrocarbon gases, and the detection of dissolved petroleum hydrocarbons. The possible explanatory variables for this site, located adjacent to the oil field, include the proximity to waste disposal wells located within 4,000 feet, where 12.5 million barrels have been injected between 1977 and 2017. However, and this is an important addition, the high concentrations of many of dissolved manufactured volatile organics not associated with oil field sources suggest there is also an industrial source affecting the groundwater at this site. And a more conclusive interpretation of sources and pathways at this well cannot be performed at this time because not all laboratory analytical data for this sample has been received. Evidence for produced water at ZR13 is provided by the major ion chemistry, the ammonia, presence of ammonia, dissolved organic carbon, minor ion ratios, and enriched carbon-13 isotopic values. Possible explanatory variables for this site located adjacent to the oil field include the historic surface pond disposal in the Casamiglia field to the west, which is documented to have affected groundwater in this area. This table here shows lists of methane isotopic values, methane concentrations, and the concentrations of ethane, propane, and isobutane at ZR2 and ZR3. These methane concentrations and isotopic values, in combination with trace amounts of the light hydrocarbon gases, are geochemical indicators of the presence of thermogenic or mixed microbial thermogenic methane gas at these two sites overlaying the Orcutt oil field. So with these additional geochemical indicators, evidence for oil field fluids, which are produced water and the thermogenic gas at these two sites, is provided by the major ion chemistry, minor ion ratios, the methane isotopes and concentrations, and the light hydrocarbon gases. Possible pathways, possible explanatory variables at these two sites overlaying the oil field include 10 abandoned oil wells within 1,600 feet, with 3 of those wells potentially not abandoned properly, 23 injection wells within 3,200 feet, with a total injection volume of 14.7 million barrels between 1977 and 2017, and mapped faults. Now let's look at the potential pathways for the migration of the produced water at the sites adjacent to the oil field, okay, based on the evidence and explanatory variables. So for ZR16, potential pathways include legacy surface disposal or injection into formations that are hydraulically connected to the shallow groundwater, since this site is located adjacent to water disposal wells. Again, however, we cannot fully assess the pathways at this point because we don't have all the data back. And one of the data sets that we're waiting for is noble gases, which may help us to distinguish between subsurface and surface sources or pathways for produced water found at this site. For ZR13, the potential pathways include the percolation from historically documented surface pond disposal. For ZR2 and ZR3, the potential pathways for co-occurring produced water and thermogenic gases at these sites overlaying the oil field include upward flow of oil field fluids through formations, leaky wells or well bores allowing flow across confining layers, or movement along nearby mapped faults. So the significant findings of the regional groundwater program for the wells adjacent to and overlaying the Orcutt oil field are: at ZR16, concentrations of the inorganic and organic constituents provide multiple lines of evidence for mixing of ambient groundwater with produced water and an industrial source. For For ZR13, concentrations of inorganic constituents and carbon-13 isotopic values are consistent with mixing of ambient groundwater with produced water from historic surface pond disposal. For the wells overlying the Orcutt oil field, ZR2 and ZR3, methane concentrations and isotopic values, the combination of inorganic constituents and the light hydrocarbon gases provide evidence for upward movement of the produced water and thermogenic gases through formation or along leaky wells, wellbores, or faults, and mixing with the overlying groundwater. All other sites and historic data with more limited analytes showed no existence of any oil field fluids present in the groundwater. Okay, so other activities influencing water quality in the area of the Orcutt oil field that are not related to oil and gas activities are recharge from irrigated agricultural land, which is widespread in the area, and rock-water interaction. For the wells sampled as part of the monitoring program, ZR15 showed evidence of recharge from irrigated agricultural land based on nitrate concentrations greater than 5.5 milligrams per liter and increased concentrations of chloride and boron and slightly enriched stable isotopic values, or stable isotopes of water. Other wells that exhibited similar evidence of irrigation return flow, which are shown with the circles, okay, are mostly shallow monitoring wells located along the San Antonio Creek and Harris Creek. Evidence for rock-water interactions exhibited at some sites is based on the general pattern of increased TDS and inorganic concentrations with depth and groundwater age. The last topic of my talk is information gaps and future priorities. This graph shows the elevation of perforated intervals for groundwater wells and produced water wells displayed along a north-south section across the oil field, and illustrates one factor limiting this study was the major spatial information gap created from the lack of wells available for sampling groundwater overlying and in some areas adjacent to the oil field, and that's shown with this circle. And geochemical indicators of oil field fluids useful for this study, which are not readily available in historical data sets, such as light hydrocarbon gas concentrations and isotopic values, dissolved organic carbon, carbon-13 isotopic values, and groundwater age, create spatial data gaps in areas overlying and downgrading of the oil field. Major and minor ions were also useful, are widely available, but not always with complete spatial coverage, and other areas lacked wells available for sampling. And the areas that we lacked sampling are shown here with these circles. In conclusion, the summary of findings for this study are, for the oil field fluids in groundwater, 2 of 16 groundwater samples had evidence of produced water. 2 of the 16 groundwater samples had evidence of oil field fluids in groundwater. Evidence included inorganic and organic constituents and carbon-13 and methane isotopes, and spatial and vertical data gaps did exist. Other factors influencing groundwater quality included irrigated agricultural land as a source of recharge for both groundwater basins. Most groundwater is pre-modern. Carbon-14 groundwater age is approaching 30,000 years before present. It's the oldest groundwater we sampled in the San Antonio Creek groundwater basin. Rock-water interactions and oxidation reduction conditions are the primary processes influencing water quality, and microbial methane gas is widely present in the San Antonio Creek groundwater basin, and I didn't show that data. And a final thought, new wells and additional monitoring of areas with information gaps in the future may yield additional insights. And with that, I'll take questions.
We have a question from Preston Jordan with Lawrence National Lab. He asks, what was the threshold above mean for the major ion concentrations to be indicated by an up or down arrow? And he thanks you for the work.
Well, the up just suggests that the concentration was above, and the down arrow suggests concentration was below the mean. And the mean was calculated by taking concentrations of all the wells, calculating an average value, and then just determining whether or not these concentrations were higher or lower.
So since you asked for the threshold, that's any above the mean and any below the mean, there isn't some threshold it needed to hit to have an up or down arrow?
If it's above the mean, it's a up arrow, and if it's below the mean, it's a down arrow. No, just the samples we collected. So I was just comparing the samples collected during our study. And those 4 wells happen to have higher concentrations than what we measured generally in all the other wells. Did somebody else have a question? The only one from Preston.
We had a question for our previous speaker that came in right after we transitioned on the Oxnard study. So this is from Preston Jordan, and he thanks you and asks, did constituent results other than for gases and gas liquids provide further indication of or insight regarding migration?
Well, we only had the 3 wells. We don't have enough wells to really answer that further. Part of the future monitoring would be to put more wells in to be able to answer that question better, to be able to trace them perhaps in multi-depth, in a multi-depth well.
Oh, wait.
Yeah, I just had a quick question. Well, I guess, or maybe a comment. So you had on this the conclusion slide evidence of produced water in the wells, but what I saw in there was evidence of some water with some oil and some constituents that are similar of the formation in those wells. Produced water would be to mean that you had produced water from a well and then it got somehow into the groundwater. But the fact that these are groundwater wells that are in close proximity to the oil field, what I kind of see lacking is looking at other potential sources besides just produced water that could explain some of those geochemical signatures. So, were things like, one well you did have a historical surface impoundment as a possible source. Are there other surface impoundments in the area that were looked at? Were there natural seeps in the area? A lot of these oil reservoirs are kind of continuums between where there's groundwater and there's groundwater that has oil in them, which is an oil reservoir. So I guess where I can get troubled is when you call these things produced water, that has a very specific meaning, meaning that there was somehow a pathway for that contaminant to have gotten there from oil production as opposed to have gotten there just naturally.
Okay, so let's see, that's a long question, but so basically, it's the combination of all the geochemical indicators that I tried to outline in that table and then discuss throughout the presentation that really eliminates a lot of other natural sources. So it has now, the definition of how we're using the word produced water, that's the way it's being used. It doesn't necessarily, I don't know if it's implication, it's water that's, you want to say something about the terminology, I guess, of how we use produced water, but that's the whole gist of the discussion is that taken on its whole, the combination of all the different geochemical indicators and then taking into consideration all the explanatory variables, that's how we're coming up with concluding that it is in fact produced water. Yeah.
Yeah, I think it might help to define the terms a little more. We are using produced water. Produced water could include water pumped out of oil wells, or it could include formation waters. So that might be the key difference in the terms as we're using them. We're using produced water to represent waters that could be affected by an oil field source. So that might be the difference or a key distinction to make. So your point's well taken. Does that address your question? That was the key.
Yeah, I guess it has to just be a little bit clear because produced water has a very specific meaning, and how it's been used interchangeably in a lot of these discussions is just water that has some either oil or brine that is associated with that oil field reservoir. But one possible way is you talk about all the different pathways, but a lot of the discussion is just linking, hey, look, this chemical constituent that you're finding in groundwater is what you also find in the oil field, but how did that actually get there? A lot of these geochemical indicators aren't going to tell you the pathway. I know we talked about maybe the noble gases as a potential way that's going to talk about that, but otherwise, I think you have to be careful how you use produced water versus just water that has brine and oil in it, because they mean different things.
Yeah, we can do that. We can make clarifications on what those terms mean. Yes, it really is referring to dissolved, to oil field waters. And with the way that we can tell the difference about pathways, and you'll see some more examples of this, is by analyzing the co-occurrence patterns of different constituents, which indicate something about pathways.
Hey, Matt.
In some cases.
Matt,
Yes.
John. So Daniel, I want to make sure that I'm understanding what you're saying. So is what you're saying is that basically the in situ aspect of where there's water, naturally occurring water or injected water mixed in with oil versus when it's pulled out of the ground? That the distinction being that when it's out of the ground, it would be considered produced water as opposed to how you're describing the groundwater that has oil constituents in it.
Yeah, I think
So it's a temporal location type of.
produced water is water that's been produced out of a well, de-oiled, and then it's either injected into the ground as a wastewater, or if it was put into a surface impoundment, or if it leaked at some point after it was produced. But when we're looking at these and we're seeing, hey, these are evidence of, or these are waters that do have, similar chemical composition as produced water, doesn't necessarily mean that they're produced water. I mean, it could either come from just naturally leaking out of the formation in seeps or through faults, or it could be a leaking well, or all the different pathways that you described. But when you're saying there's evidence of produced water, that's not evidence of produced water. That's evidence of water that has some type of similar composition as produced water. It doesn't actually, in all cases, guarantee that you understand what the pathway is. So, am I?
I think I understand what you're saying. So there's a distinction between water that's injected that came from a oil well. The water that came from that would be considered produced water. It could have been re-injected. So it also could be a situation where the water is circulated back through. So I guess what I'm hearing you say is that there needs to be in your opinion, there needs to be a distinction between that mixed piece versus the natural, undisturbed portion of the formation that has oil and water in it, which I don't know if it even exists. That might be something that would be really difficult to find. But I think that there's multiple lines of evidence that are being put forth. So the age dating aspect of it may come into play and other chemical constituents.
Daniel, let me echo what Matt said. We need to clean up our language a little bit, and we need to make clear when we know it's an oil field fluid, and when we know it's produced water, because sometimes we can distinguish those pathways, and we just need to clean up and tighten up those words a bit.
Yeah, sure. I think they've been kind of used interchangeably.
Right, we have, and we need to tighten it up.
All right, thank you.
I think this is all a very good discussion. Thank you. Thank you, Robert. Our last presentation of the day is from Pete
I had a
McMahon.
follow-up question on Oxnard.
Okay.
So
I was trying to escape, sorry.
this is a follow-up from Preston.
Sure.
And his question regarded if and what results from constituents other than methane and higher carbon count compounds indicated. For instance, the major ions and minor constituents. And he thanked everybody for answering his questions.
So he's asking me what else did we see to verify that that was a thermogenic signal?
I think he's asking, aside from methane and the higher carbon count, what were the results for other constituents and what did they indicate? For example, what did major ions indicate and the minor constituents?
When we did like plots of minor ions to like the local meteoric water line, they didn't have a clear signal of that mixing. We only had signals for gases. We also looked at dissolved inorganic carbon isotopes, and that also, I didn't show those other isotopes that we saw, but those also show just a clear signal of a thermogenic in 2 of the 3 wells. But the minor ions really will tell you about mixing and not necessarily anything with the gases.
I guess how I was understanding Preston's question is he was asking overall what were the results of analyzing for dissolved constituents, dissolved in water. So you reported the results with respect to the thermogenic and thermogenic mixed gases. Overall, you didn't find from looking at dissolved constituents in water, solutes, major ions, ion ratios, we didn't see any distinct evidence that indicated the presence of oil field waters in these groundwaters. Is that a fair statement, Celia?
Yeah, so we had no indication of any petroleum hydrocarbons, any of the inorganic constituents. They showed no mixing.
Okay, thank you. Our final speaker is Pete McMahon. Pete is a research hydrologist with the U.S. Geological Survey, Colorado Water Science Center. He spent the first 8 years of his USGS career in the South Carolina Water Science Center, where he also earned his PhD in geology from the University of South Carolina at Columbia. He has more than 30 years of experience conducting groundwater quality studies across the United States. He is currently collaborating on energy-related groundwater studies in California, Colorado, Montana, North Dakota, New York, and Pennsylvania. And Pete will be speaking about radium in groundwater related to oil and gas production in the southern San Joaquin Valley. Thank you.
Thanks, Karen. Let's see. Matt already talked about the purpose of the regional monitoring program, so I'll skip this slide and jump right into a summary of our findings before I get into the details themselves. In and near the Fruitvale oil field, radium-226 plus 228 activities are low, and none of the samples exceed the drinking water standard, or the MCL, which is 0.185 becquerel per liter, which is the same as 5 picocuries per liter, if you're more familiar with those units. However, in and near the Lost Hills and South Belridge fields, radium activities are higher, and samples from 27% of the wells exceed the MCL. Radium activities in groundwater are controlled by salinity, redox, and pH. The high radium wells contain up to about 45% oil field water from surface and subsurface sources. The highest fractions of oil field water appear to be from leaking oil field water disposal ponds. Radium in samples affected by those ponds isn't actually from the oil field water, rather it's mobilized from aquifer sediments by reaction with that oil field water.
Here I'm showing our study areas. There's the Fruitvale oil field on the east side of the valley, and we sampled 14 water wells over there. The well types are shown to the left. All those wells are completed in alluvium. We sampled 26 water wells in the Lost Hills and South Belridge fields. 7 of those wells are in alluvium, 17 are in the Tulare Formation, and 2 wells have unknown aquifer designations. Can you guys see that laser pointer? Yeah, okay. So this graph just shows the distribution of radium activities in groundwater on the left side of the plot and in the associated oil field water on the right side. And I'm using, the activity distributions are being represented by box plots. The definition of a box plot is shown over here in terms of percentile concentrations. For the Fruitvale oil field, and also for the groundwater, I'm showing the results for the individual water wells that we sampled by the squares, circles, and triangles. In the Fruitvale oil field, radium activities in groundwater are significantly lower than the activities in the Lost Hills and South Belridge study areas, and none of the samples have activities above the MCL. But in the Lost Hills and South Belridge fields, 27% of the samples do exceed the drinking water standard, which is represented by that horizontal line marked as MCL. 14 of our 40 samples were actually from drinking water wells, but none of those 14 samples had radium activities above the drinking water standard. And then for each of the oil fields, radium activities in groundwater are significantly lower than the activities in oil field water. Well, our data show that radium activities in groundwater are controlled by salinity, redox, and pH. So for example, we observed a significant positive correlation between TDS concentrations and radium activities. And a number of different studies have shown that saline groundwater can actually cause radium to be desorbed from sediments and put into solution by the so-called competing ion effect. And this is just where cations like calcium and strontium in the saline water will outcompete radium ions for adsorption sites on sediment, causing that radium to go into solution. We also observe a significant positive correlation between manganese plus iron concentrations and radium activities in groundwater. It turns out that manganese and iron oxide minerals can retain or adsorb a lot of radium on their surfaces. And again, a number of different studies have shown that that radium can be mobilized in anoxic groundwater due to manganese and iron reduction processes. And then finally, we observe a significant inverse correlation between pH and radium activities. It turns out adsorption of radium onto sediments is affected by pH, and sediments have a reduced adsorption capacity for radium at lower pH. Here I'm showing the spatial distribution of radium in groundwater in the Lost Hills and South Belridge fields. The sampled water wells are shown by the large blue and red circles. Oil and gas wells are shown by the little gray dots. The green shows active or decommissioned oil field water disposal ponds, and the pink lines are faults. So the water well symbols are color-coded according to their radium activities, and the red circles show the water wells that have radium activities above the drinking water standard. And so there are 4 of those types of wells in the Lost Hills study area, here, 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 and here. There are 3 of those wells in the South Belridge study area, 1 here, out here, and down here. And so we use multiple lines of evidence to bin these 7 high radium wells into 4 different groups that were characterized by the amount and source of oil field water that was mixed into those samples. Mixing with oil field water is relevant to our discussion because it affects salinity, redox, and pH, which we know affects radium mobility in groundwater. And so one of our groups consists of wells or samples that had 10% or less oil field water from some type of subsurface source mixed into the sample, and those 2 wells are circled by these big black circles here. There was another group that had little or no oil field water. Those wells are circled in green. There's a group that has about 40 to 45% oil field water from a surface source. Those 2 wells are circled in red. And then there's a group that had about 40% oil field water from what appears to be both surface and subsurface sources. And that 1 well is circled in orange right here. And so I talked about multiple lines of evidence. And so here I'm showing examples of 8 lines of evidence that we considered to bin these samples into the 4 groups. And so I'm showing those the characteristics of those 8 factors for each of the groups. And so, for example, if we look at the group that had only had oil field water from a subsurface source or had essentially no oil field water, those samples had no tritium, they had low carbon-14, and where noble gas data were available, they're enriched in helium-4. So water in these 2 groups is really old water. In contrast, the 2 groups that had some or all of their oil field water from a surface source, those samples contain tritium. And where noble gas data are available, those noble gases appear to be equilibrated with the atmosphere. So those 2 groups had at least a component of water that was both young and recently exposed to the atmosphere. If we consider the 3 groups that had some oil field water in them, so these 3 here, they had concentrations of chloride, bromide, and lithium ranging from somewhat elevated for this group that had less than 10% oil field water to elevated for these 2 groups that had larger fractions of oil field water. All 3 groups had detections of BTEX compounds. For these 2 groups, where some or all of the oil field water was from a subsurface source, they have high concentrations of thermogenic methane, and so this is the methane that's co-produced with oil in these study areas. In contrast, this oil field, this group where all the oil field water is from a surface source, it had very low concentrations of methane, and that methane is biogenic in origin, so it was produced in the near surface environment. And then for this group that had essentially no oil field water, had the lowest concentrations of chloride, bromide, and lithium, no BTEX compounds, and either no methane or very low concentrations of thermogenic methane. And then just one more example. For these 2 groups that had some or all of their oil field water from a subsurface source, each group had a large number of oil wells and injection wells and oil field water injection volumes within 500 meters of those sampled wells. So these 2 groups here. However, this group where all the oil field water is from a surface source just had well, all of them were 3 kilometers or less down gradient from an active or decommissioned disposal pond. There were just a few oil wells and no injection wells within 500 meters. And then for this group with essentially no oil field water mixed in, there were no oil wells or injection wells within 500 meters. And so for these 2 groups here, given all of the oil wells and injection nearby, we might think that the oil field water in these samples is from oil and gas production. But as I note down here, and as has already been discussed during the previous talks, vertical separation between the bottom of water wells and the top of oil wells, the perforations, is relatively narrow for these 2 groups. And so it's entirely possible that some of the mixing that we see in these 2 groups is due to natural processes over geologic timescales. And so it's those groups that have some or all of their oil field water from surface sources. So these 2 groups here, where we can associate the oil field water mixed in those samples with oil and gas production activities. And here I'm just showing the locations of the wells in those two groups. So these are the two wells that are in that group where all of the oil field water is from a surface source. And I'm circling not only the two wells that we sampled, but also what we believe to be the contributing upgradient disposal ponds. And then this is the location of the well in that one group where oil field water seems to have both surface and subsurface sources. So, you know, I didn't indicate, but I'll go back and do so right now. Oops. I just messed something up. Bear with me. All right. So the water in these groups has, you know, roughly 40 to 45% oil field water in them. And we determine the amount of oil field water in those samples using data like these. And here I'm just showing boron and chloride concentrations for those 3 high radium wells that I just talked about in the green, pink, and blue triangles. And each of those groundwater samples is associated with a mixing line of the same color. And the mixing lines are defined at the low concentration end by more dilute groundwater in the South Belridge field, indicated by these gray triangles. And then at the high concentration end, the mixing lines are defined by the chemistry of what we think is the upgradient disposal pond. So for example, this well BG7 in green is associated with the green mixing line, and this upgradient pond, sample BGW4A, is associated with the blue mixing line and these blue data. And just to remind you where those two wells are located, 7 is here, 4A is here. It turns out that the radium in these samples isn't actually from the oil field water. Rather, it's mobilized from the aquifer sediments by interaction with that oil field water. And we base that conclusion on data like these. Here I'm showing radium-228 to 226 activity ratios versus chloride concentrations. And data for those Belridge groundwater samples that had lower radium activities are shown in gray. Data for those 3 samples with high radium activities are in red. Data for 2 disposal ponds at the south end of the South Belridge field that we sampled are shown in green. And then other oil field water are shown in black. And you can see that the activity ratios for those 3 high radium samples in red, they look a lot more like the activity ratios in that dilute groundwater in gray than they do to the oil field water in green and black. So how do we rectify or resolve this apparent conflict between these 3 high radium samples that have a lot of oil field water mixed in with them, yet the radium isn't from oil field water? And so my few remaining slides are a series of cartoons that will try to explain what's going on. Here I'm showing an unlined disposal, oil field water disposal pond that receives water that has high concentrations of things like radium, overall salinity, dissolved organic carbon, barium, manganese, and iron. When that water infiltrates into the subsurface, it could mix with the underlying groundwater. And the ambient groundwater generally has much lower concentrations of radium, overall salinity, dissolved organic carbon, barium, manganese, and iron, but it has higher concentrations of sulfate than the oil field water disposed of in the ponds. And so the first step is you have to get rid of the radium that was in the pond water originally. And when you expose that oil field water to air in the near pond environment, it oxidizes the manganese and iron in that water, causing manganese and iron oxides to precipitate. And that radium can be removed from solution by adsorption onto those manganese and iron oxides. In addition, when you mix the high barium pond water with the high sulfate groundwater, it causes barite precipitation. And radium can be removed from solution by co-precipitation with that barite. The next step then is to add radium back into the water. And so even though you've taken the radium out of that pond water, you're still left with the high salinity, high DOC water that's moving farther down gradient into the aquifer. And that promotes radium desorption from sediments by the competing ion effect, which we talked about earlier. And also, in the anoxic water, you're dissolving manganese and iron oxide minerals in the aquifer sediments, causing additional radium mobilization to occur. And the microbial processes associated with that manganese and iron reduction, if I said oxidation earlier, I meant reduction, sorry about that. Microbial processes that are reducing manganese and iron in the aquifer are also producing CO2, which lowers pH in the groundwater and further mobilizes radium from the sediments. And so just to summarize, again, in and near the fruit oil field, the radium activities are low. None of the samples had activities above the drinking water standard. In the Lost Hills and South Belridge fields, the radium activities are typically a lot higher, and 27% of the wells had radium activities above the drinking water standard. Importantly, radium activities are controlled by salinity, redox, and pH. And the high radium wells contain up to 45% oil field water from surface and subsurface sources. The highest fractions of oil field water are associated with leaking oil field water disposal ponds. The radium in samples affected by those ponds is not actually from the oil field water itself, but rather it's mobilized from the aquifer sediments by reaction with the oil field water. And thanks for your time. I'm waiting for that question.
No questions? Thank you. Thank you. And we have some closing remarks from Matt Landon.
Okay, well, thanks, and thanks for everyone hanging in there. Let's see. It may take me 5 minutes to switch presentations because I can't find the mouse. Okay, oh, there we go, thank you. Okay, that works much better.
Where's yours?
Cool, I'm going back to one. We're gonna do one all over again. Well, thanks. We'll just close with some general observations. And, yep, oh, thank you. Cool, thank you. All right, some lessons learned, notes on some limitations the program's been facing, and we'll close by just with a preview of some results from the first multiple well monitoring site that was drilled for the regional monitoring program, which was adjacent to the Lost Hills site. Okay, so what has the regional monitoring program been able to accomplish? In previous stakeholder meetings, we've given presentations and have publications out in which we've demonstrated mapping protected groundwater and showing relations of salinity to depth, recharge, stratigraphy, faulting, and in some cases, changes in salinity through time. That work is based upon an analysis of a combination of available water sample data, borehole geophysical log analysis, and newly collected airborne geophysical data. With respect to water quality analysis, you heard multiple examples today of using multiple lines of evidence to identify the presence or absence of oil field fluids in protected groundwater that we can sample. Here I'm using oil gas fluids to include both oil field water and thermogenic gas. Based upon co-occurrence patterns of those constituents, in some cases, we can explain why detections occurred. For example, stray thermogenic gases, as distinct from oil field water, leaks from or movement from below from formation waters or up leaky wellbores superimposed on regional groundwater flow, produced water disposal from surface ponds, of which you've heard several examples from Pete's talk and the preceding talk, and potentially movement of oil field fluids, both oil field waters and thermogenic gases from formations underlying groundwater wells. And then we can compare effects of oil field development on water quality to other sources and processes near these groundwater systems adjacent or overlying oil fields to compare effects of oil field activities or movement of fluids from oil field sources to other processes affecting groundwater quality. And these kinds of approaches get applied at multiple scales. Some of the lessons learned, hydrogeologic setting plays a large role in the occurrence of oil field fluids in groundwater. For example, we see different signals, in some cases overlying oil fields versus adjacent to oil fields, reflecting differences in the potential sources that could be affecting those waters and the constituents associated with those different sources. Mining historical water sample data, oil well data, and injection records has provided key data for evaluating relations of water quality to potential risk factors, and that continues to be a major emphasis of the program. And we also have been installing, as I noted, new multiple well monitoring sites, and these have added some insight on fluid movement in deep aquifers adjacent to oil zones. I'm going to be showing an example of that in a moment. Some typical limitations of what we're seeing in the regional monitoring program data to date. We're continuing to compile a great deal of, I lost my mouse again, I'm sorry. There we go. Great deal of historical data from scanned water and oil well records into numerical data sets for use in analysis and publishing those data in data releases. However, this is a very laborious, slow process, and so certainly is a major consumption of resources involved in compiling those numerical data sets. We've had historically some limitations in access to operator oil and water wells. In 2018, we moved to a process of providing written summaries of oil field development history, description of major fluid movements within oil fields, and major fluid types that we would expect to occur within oil field environments, using that background information to inform sample site selection criteria used in picking sampling sites within oil fields and suggested sampling sites, and then running those written descriptions by operators, getting technical input on final site selection. That process has been productive to date and is continuing. Other limitations include limited pressure data available to evaluate movement of fluids between production zones and groundwater zones. Although you heard David Shimakuro's talk today describing a proxy approach for trying to estimate fluid movement using a net fluid volume balance approach. Based upon groundwater sampling so far, the density of sampling data tends to be fairly low, as might be expected for a regional program trying to cover large areas. We try to utilize existing wells first, because that's cost-effective approach to a sampling program, but that inherently leaves gaps in terms of where wells are available for sampling. And particularly leaves gaps with respect to having deep wells for characterizing aquifer chemistry overlying and near oil fields. And so for that reason, the regional monitoring program includes some drilling and installation of deep multiple well monitoring sites at selected high priority locations. We can only do this at some locations. And next, I'd like to briefly describe some results from the multiple well monitoring site that we drilled adjacent to the Lost Hills oil field last year. Okay, so to date, we have drilled 2 multiple well monitoring sites, one located adjacent to the Lost Hills oil field, which is the red star, another located adjacent to the North and South Bell Ridge oil fields, which is the yellow star. The Lost Hills site was drilled in March and April of 2018. The Bell Ridge site was drilled in July and August of 2018. Both of these sites were selected primarily to fill gaps in available information on the groundwater conditions in these areas, adjacent to oil fields and lateral to areas of intense development within the oil fields themselves. And today I'm just going to present some results from the Lost Hills site. Equivalent information from the Bell Ridge site we anticipate will be available in the near future. So at the Lost Hills site, which was drilled to a depth of about 1,850 feet, collected a broad suite of geophysical logs, borehole geophysical logs, and detailed analysis of the geologic materials encountered, and we're able to determine the depths of key clay layers that may act as confining units and affect groundwater flow, as well as formation boundaries. And all of these results will be included in a forthcoming USGS report by Rhett Everett and others. And so we identified the depths of the Corcoran clay, Tulare clay, and Nicola clay in the base of the Tulare formation. We installed 5 wells in different major aquifer layers. So the deepest well near the base of the Tulare, well number 2, wells are numbered 1 to 5 from bottom to top. Well, the second well below the Nicola clay, third well between the Nicola and the Tulare clay, fourth well above the Tulare clay, and fifth, or between the Tulare and Corcoran clay, and a fifth well above the Corcoran clay. And using these nested or wells at a single horizontal location, but wells screened at different vertical depths in the aquifer systems, we can evaluate vertical changes in water levels that indicate directions of groundwater flow vertically, and we can analyze changes in water chemistry between different aquifer layers to assess vertical movement within this aquifer system. So let's look at water levels. So here's an example. This slide is showing on the x-axis the measured depth to water in each individual well, feet below land surface, in these 5 wells. And on the y-axis is the depth to the top of perforations of each well. And so we see differences in the water levels in this group of wells, 5 wells, at different depths in the aquifer, ranging from approximately 50 feet below land surface to more than 250 feet below land surface. And so what these differences in water levels are indicating is potential directions of groundwater flow between aquifer layers. And based upon these measurements happen to show measurements that were made on October 10th of 2018, but the data collected through time at this site shows similar patterns over time, is that groundwater flow is generally downward in the upper part of the system into the zone about a little bit more than 600 feet deep. And then groundwater flow gradient would be upward from the deepest part of the system into the middle portion of the aquifer system. And this is consistent with what we would expect based upon where we would see most of the groundwater development in the region, which would be in the middle portions of the system, further to the east and down gradient. But it tells us something about directions of groundwater flow and interactions between different aquifer layers. Another way to look at this is to look at changes through time in water levels. This axis, or this plot, showing changes in water levels relative to the water levels in each well that were measured on May 31st of 2018, and how the water levels in each individual well changed through time after that. So change in water level in each of these wells is shown on the y-axis. So in the deepest well, number 1, the blue line, we saw an increase in water level over this several-month period, a rise of nearly 8 feet in water level. In contrast, over the same period, in the shallowest well, number 5, and in the second deepest well, number 2, we saw a decline in water level of less than half a foot. And in the middle wells, number 3 and 4, we saw declines in water levels of up to 10 feet over the same period. So we see water levels in some of these different aquifer layers moving in different directions. The declines in water levels in the middle wells, 3 and 4, are more what we might expect as a function of groundwater pumping during a summer irrigation season, further down gradient. But the water levels that we see in well number 1, the deepest well, the base of the Tulare, are very different. And those water levels must be responding to some other system or activity. Possibly it could be in response to oil field activities up gradient of the system, up gradient of this well. But we see these water level dynamics tell us something about how the aquifer system is responding to nearby stresses. Briefly, in terms of water quality, all of these wells are in the process of being sampled. So we don't have, excuse me, final data from these sites. But we could look at water quality based upon the borehole geophysical logs that were collected, which total dissolved solids was calculated from the borehole resistivity records and other borehole geophysical logs using a Bateman and Conan approach. These are the blue dots and a blue smooth line. The green dots and green line represents total dissolved solids of water in samples collected from the individual monitoring wells after development of these wells, and calculating to total dissolved solids from the electrical conductivity measured in the water. So in general, total dissolved solids in all of these sites was less than 10,000 milligrams per liter. In the water sample from the deepest well, the total dissolved solid was calculated to be about 6,800 milligrams per liter. And in the second shallowest well, 2,100 milligrams per liter, all below 10,000 milligrams per liter. There were some depths with sandy sand layers, clean sands, where the TDS, total dissolved solids, was calculated to be greater than 10,000 milligrams per liter, both in the shallower part of the system and deeper part of the system. But most of the data show total dissolved solids being less than 10,000 throughout the system. Again, we'll have a lot more information and have the full set of tracers to better understand this system once we get the sampling results back and get the sampling completed. In general, this data, I want to note, is available online from websites shown here. You can download all the water level data, both manual, discrete measurements made on approximately monthly intervals, and hourly water level data from recorders in the wells from USGS websites. You can also download all the geophysical logs, lithologic logs, and well construction information from these sites, from websites. This is all available for the Lost Hills site at this point, and equivalent information will be available for the Bell Ridge site in the near future. So just wanted to give you a quick preview of the drilling results, and we anticipate more of those in the future. And that kind of wraps it up for what we plan to talk about it. Again, thanks very much, everyone, for being here, and thanks for people online, and really appreciate everybody coming out today. So, and we take any additional questions that we didn't already cover.
That concludes our stakeholder meeting for today. We'll be continuing to hold these semi-annually, and so expect another announcement in the June timeframe.
Karen, I just got a question in.
Oh, yes. Matt, don't go too far away.
Yes. It's about the well number 1 water level curve. This appears to be a well recharge curve due to low permeability formation rather than actual water level change. Could this screen have either ended up in an aquiclude or be in a more permeable zone compartmented?
Yeah, that's a great question. That was a very low permeability zone, well, relatively low permeability zone compared to all of the other zones. We did do hydraulic testing in all of these wells, and that well number 1, the deepest well, had by far the lowest hydraulic conductivity. It was extensively developed. The well does yield water, so we did extensive development of the well screen, pumped the monitoring well a long time to get all the fine particles out of the formation. And so it does reliably yield water, and we can pump it and can collect samples from that location. But certainly it is, there's no question that it's got a very different response than the other layers in the aquifer system. So in general, yes, it's a much lower hydraulic conductivity layer near the base of the Tulare, and it is a layer that does not respond the same as the other shallower layers in the formation. I hope that answered the question.
Thank you. Thanks. Just a few closing remarks. I want to make sure that everyone is aware that this meeting is going to be posted. You can look at the agenda, and it's on the Water Board's website. We'll have the recording posted there. And so, as I said, our next meeting will be in the June timeframe. We would appreciate your feedback. There's a questionnaire at the back, on the back table. If you have any input for us, please do provide it. And that concludes our meeting. Thank you for coming. And thank you, USGS.